In September of 2015, a single signal lasting less than 1 second arrived at 2 detectors in the United States after traveling for over 1 billion years across the universe. It was the first time in human history that we had ever directly detected a gravitational wave, a ripple in the fabric of spacetime itself, caused by 2 black holes colliding somewhere in the distant past. That one signal was the entire discovery. It made global headlines. Scientists opened press conferences with the words, "We did it." 11 years later, that same global network of detectors just added 161 new detections in a single release. The total count now stands at 390. Now, what was once a once-in-a-decade miracle is now happening 3 to 4 times a week. So what changed? What is this new data actually revealing about black holes we've never been able to study before? And why are scientists calling some of these objects black holes built from other black holes? If you're the kind of person who finds this stuff genuinely fascinating, rather than just background noise, you're exactly who this channel is for. Stick around, because this one gets stranger the deeper we go, and I promise it's worth it. Let's get into the data. To understand why this new catalog matters so much, you have to understand what a gravitational wave actually is, and why detecting one is almost absurdly difficult. When 2 black holes spiral into each other and merge, they don't just collide quietly. They send ripples outward through the fabric of space and time itself, stretching and squeezing everything those ripples pass through, including, eventually, the Earth. The problem is that by the time those ripples travel across billions of light years to reach us, they've weakened to an almost unimaginable degree. The detectors built to catch them, LIGO in the United States, Virgo in Italy, and CAGRA in Japan, working together as what's called the LVK collaboration, have to measure a change in distance along kilometers-long detector arms that's smaller than the width of a single proton. To put that in perspective, that's like trying to measure a change in the distance between here and the nearest star that's smaller than the width of a human hair. It took decades of engineering and years of painstakingly filtering out noise from earthquakes, passing trucks, and even ocean waves crashing on distant shores just to make a detection like this possible at all. This newest release, called GWTC 5.0, the 5th Gravitational Wave Transient Catalog, adds 161 new confirmed signals gathered during a 10-month observing run, stretching from April 2024 through the end of January 2025. That single observing run alone accounts for roughly 75% of every gravitational wave detection ever recorded since 2015. Let that sink in for a second. Over a decade of gradually improving detector sensitivity has led to a point where a single 10-month window can produce 3/4 of humanity's entire dataset on these events. That's not incremental progress, that's an exponential curve, and it's happening because every small improvement in a detector's sensitivity doesn't just modestly increase its range, it exponentially increases the total volume of space it can effectively monitor at once. Buried inside this catalog are several individual detections that are genuinely record-setting on their own. One event, recorded on June 15, 2024, and designated GW240615, was picked up simultaneously by both LIGO detectors and Virgo together. Having 3 separate detectors catch the same signal allowed scientists to triangulate its position with extraordinary precision, narrowing the source down to a patch of sky just 6 square degrees across, the tightest localization for a gravitational wave event ever achieved. To put that in context, 6 square degrees is roughly the area covered by about 30 full moons side by side, which sounds large until you remember we're talking about pinpointing an event that happened somewhere across the entire visible sky, billions of light years away. The catalog also includes what researchers are calling the clearest gravitational wave signal ever recorded, a detection so clean and strong that it stood out from background noise more distinctly than any signal before it, giving scientists an unusually pure dataset to study the physics of the merger itself. But the detail that's generating the most genuine excitement in the astrophysics community is something called second-generation black holes, and this is where things start to get genuinely strange. When astronomers first started cataloging black hole mergers, the working assumption was that most of these black holes formed the same way, through the collapse of a single massive star at the end of its life. But as the catalog has grown into the hundreds, researchers have started to notice something that doesn't quite fit that simple picture: black holes with mass and spin characteristics that look less like the direct remnant of a dying star, and more like the product of an earlier black hole merger that already happened once before. In other words, some of the black holes we're detecting merging right now may not be first-generation objects at all. They may be black holes that were themselves formed by 2 smaller black holes colliding at some earlier point, and are now merging again with a completely different partner. This is sometimes called hierarchical merging, and if it's confirmed at scale, it suggests that some regions of the universe, particularly extremely dense star clusters, may function almost like black hole factories, repeatedly building larger and larger black holes through successive collisions over cosmic time. rather than every black hole simply being the leftover core of one single collapsed star. This expanded catalog also gives scientists something they've never really had before at this scale: enough data points to treat black holes as a population and study patterns across hundreds of them at once, rather than analyzing each detection as an isolated singular event. Researchers can now look at the full range of masses across all 390 detections, from remnants under 3 times the mass of our Sun all the way up to objects exceeding 200 solar masses, and start asking genuinely new questions. Are there mass ranges where black holes simply don't seem to form? Gaps in the data that might reveal something fundamental about stellar physics? Do black holes in certain mass ranges show different spin patterns that might reveal different formation histories? The larger this catalog grows, the harder it becomes to dismiss unusual patterns as just statistical noise, and the more confident scientists can become that a genuine pattern in nature is actually being observed. There's also a broader scientific payoff buried in this data that goes beyond black holes themselves. Gravitational wave events can be used to independently measure the rate at which the universe is expanding, a number known as the Hubble constant, that has famously produced slightly different answers depending on which method astronomers use to calculate it. This disagreement, sometimes called the Hubble tension, has been one of the more persistent puzzles in modern cosmology. Every new, well-measured gravitational wave event adds another independent data point toward resolving that tension, essentially giving scientists an entirely separate method of measuring the universe's expansion that doesn't rely on the same assumptions as traditional techniques like measuring the brightness of distant supernovae. It's a genuinely elegant bit of science, using ripples from colliding black holes billions of light years away to help settle a debate about the fundamental rate at which our entire universe is stretching apart. It's worth appreciating just how quickly this field has matured. In 2015, a single gravitational wave detection was the discovery worthy of a Nobel Prize, which it later received. By 2026, a single detection barely makes news on its own, it simply becomes another entry in a growing data set. That's not a sign that these events have become less remarkable, it's a sign of exactly how much observational astronomy has been transformed in just over a decade. Researchers at the University of Glasgow, whose Institute for Gravitational Research helped build the delicate mirror suspension systems at the heart of the LIGO detectors, described this release as a genuine milestone, marking what they called the coming of age of gravitational wave astronomy as a mature scientific field, rather than an emerging or experimental one. It's worth explaining exactly how these detectors managed to catch something this faint, because the engineering involved is almost as remarkable as the discoveries themselves. LIGO, Virgo, and Kagra are all built on the same basic principle, an instrument called a laser interferometer. Each detector consists of 2 long tunnels, arranged in an L shape, stretching for kilometers in each direction, with a laser beam split and sent down both arms simultaneously. Under normal conditions, those 2 laser beams travel down their respective arms, bounce off mirrors at the far end, and return to recombine in a way that cancels each other out almost perfectly. But when a gravitational wave passes through the detector, it very slightly stretches one arm while squeezing the other, changing the distance each laser beam travels by an infinitesimally small amount, smaller than the width of a proton. That tiny mismatch causes the recombined laser light to shift in a measurable way, and it's that shift, filtered through years of noise cancellation engineering, that reveals a passing gravitational wave. Having multiple detectors spread across different continents isn't just redundancy, it's essential for figuring out where in the sky a signal actually came from. A gravitational wave reaches detectors in the United States, Italy, and Japan at very slightly different times. And comparing those tiny timing differences is exactly how scientists triangulated that record-breaking 6 square degree localization we mentioned earlier. This kind of sensitivity didn't happen overnight. The LVK collaboration has run its detectors across several distinct observing periods, each one more sensitive than the last, referred to simply as 01 through 04. The first observing run, 01, produced that single historic detection back in 2015. Each subsequent run has involved taking the detectors offline for extended periods, upgrading mirror coatings, laser power, and vibration isolation systems, then bringing them back online with meaningfully improved sensitivity. The fourth observing run, split into 2 phases known as 04A and 04B, is what produced this massive new catalog, and it alone accounts for the vast majority of every detection ever made. A 5th observing run, with detectors upgraded yet again, is already being planned, and researchers expect the detection rate to climb even further once it begins. There's also a genuinely tantalizing possibility buried in this same broader wave of research that's worth mentioning. Around the same time this catalog was released, scientists flagged an unusual gravitational wave signal that has reignited interest in something called primordial black holes, a category of black hole that, unlike every confirmed detection in this catalog, wouldn't have formed from a collapsing star at all. Primordial black holes are a purely theoretical concept, proposed decades ago, suggesting that extremely dense regions in the very early universe, moments after the Big Bang, could have collapsed directly into black holes long before any stars had even formed. If a primordial black hole were ever confirmed through a gravitational wave signal, it could help explain one of the most persistent mysteries in cosmology, the nature of dark matter itself, since some scientists have proposed that a population of primordial black holes could account for at least part of the universe's missing mass. That signal remains unconfirmed and is being treated with appropriate scientific caution. But its mere possibility shows just how much this field has expanded beyond simply counting stellar collapse black holes. This growing catalog is also becoming an increasingly powerful tool for testing the limits of physics itself. Einstein's theory of general relativity, published over a century ago, makes very specific predictions about how gravitational waves should behave, how fast they should travel, how their strength should fade with distance, and what pattern of ripples a merger should produce in its final, most violent moments. For decades, these predictions could only be tested indirectly through their effects on orbiting objects we could observe with ordinary telescopes. Gravitational wave detections let scientists test these predictions directly, comparing the exact shape of a detected signal against what general relativity predicts it should look like. So far, across all 390 detections, Einstein's century-old theory has continued to hold up remarkably well, matching the observed signals with extraordinary precision, including one particularly clean detection in this new catalog that allowed researchers to measure something called ring-down modes, the specific way a newly merged black hole settles into a stable shape after the initial collision, vibrating briefly like a struck bell before quieting down. Detecting multiple distinct vibrational modes from a single ring-down event, something achieved for the first time in this release, gives scientists an unusually direct way to test whether black holes behave exactly the way general relativity predicts, or whether there are subtle deviations that might eventually point toward new physics beyond Einstein's original theory. None of this would have been remotely possible without an extraordinary amount of patient, often unglamorous engineering work. Every gravitational wave signal in this catalog has to be extracted from an ocean of background noise, vibrations from distant earthquakes, seismic activity from ocean waves crashing against coastlines thousands of miles away. Even the everyday rumble of trucks driving on nearby roads can all interfere with a detector, sensitive enough to notice something smaller than a proton's width. Filtering all of that out reliably enough to trust a detection, especially a faint one, takes years of algorithm development and careful cross-referencing between multiple independent detectors, which is exactly why having LIGO, Virgo, and Kegra operating together as one coordinated network matters so much. A signal that shows up simultaneously across multiple detectors, each built independently in different countries using different local environments, is vastly more trustworthy than any single detector's reading alone, since it becomes far less likely that shared noise or a local glitch could explain what's being seen. So here's where this leaves us. A field that began with a single history-making chirp in 2015 now produces multiple confirmed detections every single week, and has amassed enough data to start asking entirely new categories of questions about hierarchical black hole formation, about population-wide mass and spin patterns, about the expansion rate of the universe itself. Somewhere out there, right now, another pair of black holes is likely spiraling toward each other, about to send another ripple across the fabric of space-time, one that will arrive at a detector here on Earth years or centuries from now, quietly added to a catalog that keeps growing larger every single week. If stories like this genuinely interest you, that's exactly the kind of content this channel exists to bring you, real discoveries, explained properly, without the noise. Let me know down in the comments what part of this surprised you the most. I'll be back soon with the next one. Until then, take care, and I'll see you next time.